All right, so let's see, 3.4 part 2. So before we solve any logarithmic equations, I wanted to show you an example of a type of equation. Just I want to ask you to kind of walk through solving it. What if we had, and I'm just making this up, e to the x minus 3 to the minus e to the minus x equals 1, and we wanted to solve that. How would we go about this? Any ideas? Could we factor out an e to the x? We have a yes and we have a no. Well, let's go about it. Let's think about it a little differently. How can I rewrite e to the minus x? 1 over e to the x. So I can rewrite the equation that way. Now what can I do with this side? Can I add these two numbers? What do I have to do to be able to add those two? We have to find a common denominator. So to find a common denominator, I'm going to multiply this by e to the x over e to the x, and I get e to the x times e to the x is what? E to the 2x, x plus x is 2x, minus 3, this is all over e to the x, equals 1. Now multiply both sides by e to the x to get that out of the denominator. So I get e to the 2x minus 3 equals e to the x. And now hopefully this looks a little more familiar. I subtract e to the x, e to the 2x minus e to the x minus 3 equals 0. And then to solve this one, what do? We could factor if it will factor, otherwise we'd have to use the quadratic formula here to solve for e to the x. But this is in a form then we know how to deal with. So I wanted to show you this because this combination with e to the x and e to the minus x comes up pretty frequently. I was talking to Miss Hine yesterday, or the day before, and she was talking about working on a problem in calculus that has an e to the x and e to the minus x where you had to do something similar to solve the problem. And I said, oh yeah, we're talking about exponential functions, so I should mention that in our class as well, because you'll see this combination e to the x plus and minus e to the minus x quite a bit. It comes up a lot. So I just wanted to go through that. All right, so let's remember our properties of logarithmic functions. So the ones that we're going to use today mostly are our one-to-one properties, or our one-to-one property. So we said the logarithmic function was 1-to-1. So that means log base a of x. If log base a of x equals log base a of y, then x equals y. And then we had our inverse properties, and we used those a little bit in the homework that we did on the board here. Log base a of a to the x. These are inverse functions of each other, so we say they undo each other. And then the other way around, we can say a to the log base a of x equals x. So those are the properties that we're going to use mostly today for solving logarithmic equations. And for the vast majority of logarithmic equations, we use two different methods. and they're going to be similar to what we did for exponential equations. Just doing a similar thing using logarithms. So our first technique is going to be to get the logarithm by itself on one side of the equation. So isolate the logarithm. So we're going to isolate the logarithm and then rewrite in exponential form. So isolate the logarithm, rewrite in exponential form. That's going to be one method that we use. And the second method that we're going to use is to get one logarithm on each side of the equation. And then we're going to use the one-to-one property. And our logarithms that are on each side of the equation have to be the same base. So I'm just going to put that in the parentheses, same base. So this method only works when we use the same base, and then we're going to use the one-to-one property. And I'll talk about a little bit different way to think about both of these as we go through this. But these are our two basic techniques for solving logarithmic equations. So I just want to go through a few examples of working with these ideas. So questions so far about what we're trying to do? All right, so let's start with this example. We have 2 log x equals 5. So because we just have one logarithm, I want to isolate the logarithmic function. So what do I need to do to isolate the logarithmic function? Divide by 2. So I get log x equals 5/2. Now we're going to rewrite this in exponential form. So how am I going to write this in exponential form? 10 to the 5/2 equals x. And that's my answer. X equals 10 to the 5/2. And if I plug that in my calculator, that's approximately, if I want an approximate answer, 316.228. Another way you can think about this, so we can rewrite this in exponential form. Another way we can think about this is once we get it to here, we can raise both sides to the raise 10 to the power of both sides. So I'm going just like before we took the logarithm of both sides. Now I can raise 10 to the power of both sides. So I could rewrite this as 10 to the log x equals 10 to the 5/2. So this is just another way of looking at it. And 10 to the log x is just x because they're inverse functions. So x equals 10 to the 5/2. So we can think of it either way. Either rewrite it in an exponential form, or we can think of raising 10 to the power of both sides. We call this exponentiating both sides. So that's what we did. That's what we did here. Same process, same idea, same result. So you can think of it either way. Write it in exponential form or exponentiate both sides. And we get to the same place. Questions on what we did there? That one was a nice easy example. All right. Let's look at this one. We have the natural log of the square root of x plus 2 equals the natural log x, and we want to solve for x. So what are we going to do here? We have one logarithm with the same base on either side. So since they're equal, what can we say here? Square root of x plus 2 equals x. Because these two logarithms are the same, they're the same base, then we can say what is what's inside our function has to be the same. And now how do we go about solving this? Square both sides. So x plus 2 equals x squared. Rewrite this as x squared minus x minus 2 equals 0. Now we can factor. This is going to factor to, is it x minus 2 and x plus 1? Equals 0. So x equals 2, or x equals negative 1. And what do I need to do now? I have two solutions. I need to check my solutions, make sure they work. So do either of these not work? X equals negative 1 is not going to work because this says natural log of 1 equals a natural log of negative 1. Can I take the natural log of negative 1? Negative 1 is outside the domain of our logarithmic function. So this is does not exist, or no solution. So my solution is x equals 2. And I plug that in here, and I say the natural log of the square root of 4 equals the natural log of 2, and that checks out. And I can also think about this as exponentiating both sides. I could say e to the natural log of square root of x plus 2, let me get this out of the way, equals e to the natural log x. So I'm raising e to the power of both sides, and this tells me that the square root of x plus 2 equals x. We get to the same place. So I can use a one-to-one property, or I can exponentiate both sides. Get to the same place. All right, questions on that example? All right, let's look at one that's just a little more tricky. Not too bad. Log x minus log x minus 3 equals 1. All right, so this one's a little trickier because I can't just add log x minus 3 to both sides because I have this 1, so I wouldn't have a logarithm on either side of the equation with the same base because I have that 1. But what can I do here? Let me give you a hint. Don't forget your properties of logarithms. So don't forget properties of logs. So Chad says we can write this as log, we're going to combine this, we're going to condense this to log of x over x minus 3. Subtraction turns into division, equals 1. Now what can we do? Logarithm on one side of the equation. So I can either exponentiate both sides or rewrite in exponential form. So let's write this one in exponential form. So how do I write it in exponential form? 10 to the 1 power equals x over x minus 3. And I get multiply by x minus 3 to get out of the denominator. So 10 times x minus 3 equals x. 10x minus 30 equals x, and I can solve this, and I end up with x equals 10/3 for my answer. So when you're working on these logarithmic equations, don't forget our properties of logarithms, because they can help you solve these equations sometimes. They can simplify your work, or even make it possible to solve the equation. Yes?
So what x is equal to 30 over 9?
39 is, we can reduce that to, yeah. So when you initially solve it, you get 30 over 9, and then you reduce it. All right, so let's talk about a couple of different examples that we saw on the board today that had to do with the compound interest formula. Just want to talk about a couple of examples using that now that we have a few more tools to work with. So a couple of applications, and then we'll talk about even more applications tomorrow. So this first one we call the doubling time. So the question is how long will it take? We want to double an investment at 8% continuous interest. So our continuous interest formula is what is it? Our amount equals P e to the RT. All right, so if we double our principal, so we're starting with our principal, we want to double it. What is our amount if we double our principal? If we start with P as our principal, what do we want to end with? 2P. So we want 2P equals P E, and our rate is 0.08 T. And we're solving for T. Well, this is really nice, because what can I do with the P here? I just divide both sides by P, and the P goes away. So I get e to the 0.08 T equals 2. And now how do I solve this thing? Take the natural log of both sides, or rewrite it in logarithmic form. Either way, we're doing the same thing. So take the natural log of both sides. Natural log of e to the 0.08 T equals natural log 2. Well, the natural log of e to the 0.08 T is just 0.08 T equals natural log 2. And T equals the natural log 2 over 0.08. And if I plug that in my calculator, I get about 8.66 years. The interesting thing here is the doubling time does not depend on our principal, so it doesn't matter how much we invest. All it depends on is our interest rate. So if we put any interest rate in here, our doubling time is always going to be the natural log of 2 over our interest rate as a decimal. That's our doubling time. And if we went the other way, when we talk about radioactivity, we talk about the half-life. So the half-life is a similar thing, except instead of exponential growth, we have exponential decay. And the half-life is a constant that doesn't depend on the amount of material we have. The half-life turns out to be something like this, where we get the natural log of 1/2 divided by something that's a property of the material. So kind of an interesting idea that we get this doubling time. It doesn't matter how much money we have. The doubling time is always the same. So for an 8% interest rate, our doubling time is a little more than 8.5 years. Questions there? Yes.
So the half-life was outlined in 1/2.
Basically, yes. And we'll talk about that more tomorrow. But that's essentially the half-life. And the R is something that has to do with the material. All right, so let's look at one more example. So let's say this time we have $50,000. And we want to retire in 30 years. And in 30 years, we want to have $350,000. That's 350,000. There we go. We want to have $350,000 at the end of this 30 years when we retire. So we have this big ambition of buying a motorhome and driving around the country. Couldn't do much else with $350,000. We want to know what interest rate, continuous, if we're compounding continuously, what interest rate would we have to invest? So we're talking about continuous interest. So we're still talking about our A equals P e to the RT. So what am I going to plug in where here? What's our amount that we're going to put in here? 350,000. And our principal is 50,000. E to the R is what we're trying to solve for, and our time is 30 years. So I'm going to E to the 30 R. Well, this is essentially the same problem now, isn't it? We can we're setting our dumpster on fire now. We know how to solve this. So we want to get our exponential function by itself on one side. So we divide by 50,000. So we get 7 equals e to the 30r. Take the natural log of both sides. So when we take the natural log of both sides, we get 30r equals natural log 7. And r equals the natural log of 7 divided by 30. And that's approximately 6.5%. So we see that what we're looking for here, this 7 is just the ratio between the amount that we have, the principal and the amount. That's what 7 is, and 30 is our time. So that would be that's how we can figure out our interest rate. So when you go to your financial planner and they're plugging these numbers into their calculator and they're working really hard, really this is what they're doing. Taking the natural log of 7 and dividing by 30. All right, questions? Okay, let me put the homework up, and then we have a short activity, and then we'll have some time to work. Uh-oh. Some of my numbers got erased over there, Jackson. I forgot to mention that during the drill. You have to hide over there by the side, but you can't erase the board. There you go.